My name is Omid. I'll present CherryPick, which is a system that lets you pick a near optimal cloud configuration for your big data recurring applications. This is a joint work with Harry Liu, Jianshu Chen, Shivaram Venkataraman, Ming Zhang, and my advisor, Minlan. So big data analytics are very common today. You have databases, machine learning, stream processing, all acting on large amounts of data. There are also many frameworks that users can choose from. There's MapReduce, Hive, Spark, and TensorFlow. Many of these big data jobs are recurring. They execute periodically on similar queries and data. You can think of analyzing server logs, processing ads data, or even scientific computation. It's so much so that Microsoft reports that 40% of the jobs Microsoft reports that 40% of key jobs at Bing are rerun periodically. To run these jobs, clouds offer a lot of options. There are different cloud providers that you can choose from, such as AWS, Azure, or Google Cloud. And within each provider, there are tens of machines that you can pick. Once you decide on your machine type, you would replicate it to build a cluster. So the combination of machine type and machine count gives into hundreds of possible configurations that you can pick from. Also, because there are so many of these jobs, it's not possible to have a human identifying the resource bottleneck on each of the configurations, because it's costly and it takes a lot of time. So why should you be careful when choosing a cloud configuration? In our experiments, we observed that choosing a good cloud configuration resulted in up to 3 times lower running time for the same cost and up to 12 times lower cost for the same performance target. This basically means that choosing a good config can save a significant amount of time, and it's even more important for recurring and long-term jobs. So given that there's a tremendous potential for cost saving for recurring jobs, in this work, we ask ourselves this question, that given a representative workload, can we automatically pick the best cloud configuration for it? The one that minimizes the cost given a performance target. So there are 3 challenges to this. The first is that we want to have low overhead. To get a sense on how well a cloud configuration does, you need to run it. And running costs money and time. Now, given the low overhead, it becomes difficult to achieve both high accuracy and also meaning that you want to be close to the optimal configuration, and adaptivity, meaning that you want to work across many of these big data applications. So the state of the art looks into 2 types of solutions. So you either have searching or modeling approaches. So as I said, we need low overhead. Therefore, we cannot look into every single configuration. Therefore, you might use a systematic searching approach. Something like coordinate descent, as an example, searches each resource dimension at a time and optimizes across that dimension. The problem is that searching approaches can be inaccurate. The cost-resource relation is usually non-convex across configurations. Therefore, a naive solution like coordinate descent that searches one dimension at a time can get stuck in local optimas or drop a dimension early because of bad configuration. So to get around the accuracy problems of searching, you might go with modeling approaches. There are many modeling works. So last year at NSDI, there was this paper called Earnest, which models the internal structure of machine learning applications for each specific machine type, and it works pretty well. But modeling solutions are not adaptive to the many frameworks, processing pipelines, and machine types that are out there. So far, we saw that modeling does not work for modeling is not adaptive, and searching is not accurate. So here, I'll present CherryPick, which achieves high accuracy, adaptivity, and low overhead. So the key idea of CherryPick is that to achieve adaptivity, it uses Blackbox modeling. Basically, it doesn't put any assumption on the internal structure of the application. To achieve high accuracy, it uses modeling to rank the configurations. It doesn't need to be accurate everywhere, but it's just accurate enough that lets you distinguish the best config from the worst. Finally, to achieve low overhead, it uses an interactive searching approach. What I mean by that is that it selects the next configuration based on the existing runs and does this iteratively. Now let me run you through the workflow of CherryPick. So CherryPick could start by running the job on any cloud configuration, either user suggested or randomly picked. Based on the result of running that cloud configuration, it updates and builds a black box model that captures the relationship between the cloud configurations and their cost. Based on that model, it ranks the configurations and chooses the next best config. In this case, it's the config that has the highest chance of minimizing the cost while satisfying the performance constraint specified by the user. And it does this process iteratively until the accuracy is high enough and we are satisfied. And then it outputs that config as the result. So now the question here becomes, how do we build this model, and how do we rank and choose the next configuration? To answer these two questions, we use a machine learning technique called Bayesian optimization. So Bayesian optimization has two components: a prior function that models the performance and cost of the analytical jobs, and an acquisition function that ranks and chooses the next cloud configuration to run based on the black box model that the prior function built. Now let's see this in action. I'll start with the prior function. So to set the scene briefly, in this graph, the x-axis is a set of configurations. You can imagine that each configuration is represented as a feature vector with the number of CPUs, the amount of RAM, the number of machines, etc. So naturally, it's a multi-dimensional space, but for the sake of brevity, I'm just showing one of these dimensions. The y-axis shows the cost of the configurations. So in this case, the dashed curve is actually our ground truth, the actual cost of running the job on the configuration. So here, I randomly picked two configurations and run them. Now the challenge here is, what can we really infer based on these two runs? So there are many valid functions that pass through these 2 points, and any of them can be your curve for the cost function. The trick here is that we introduced the notion of confidence interval. Basically, the prior function of Bayesian optimization gives you a confidence interval that shows where these functions are most likely located at. Now that we have a prior function and a confidence interval, we can use the acquisition function to rank the configurations. So the acquisition function builds, uses the prior function to calculate an expected improvement compared to the best config that we have found so far. I'm showing that in this graph as the purple curve here. So once you have the expected improvement, you choose the highest point in the expected improvement curve, and that would become your next run. So in this case, it's the point with the red triangle at the top. And you build the prior function. You recalculate the confidence interval based on that using the prior function, and recalculate the expected improvement, and do this process iteratively until your expected improvement is below a threshold. So why do we do this? The advantage of this approach is that we omit searching in areas that have less promising configurations. So here, I'm showing you an example of a database application that we ran on 66 different cloud configurations. And we picked the best config among those 66 configurations and also the worst config. And I'll show you how the accuracy of CherryPick changes for both of them. So you can see that just after a few runs, the confidence interval for the best configuration shrinks a lot, whereas the confidence interval of the worst config is almost doesn't change. By 13th run, we pick and run the best cloud configuration. So this is actually a sample run, so there are no stopping conditions, and the purpose was to show how the confidence interval changes. In reality, we usually converge to a near optimal config within 6 to 10 steps. There are also a few challenges in making the Bayesian optimization work for the cloud. So cloud is a shared environment, and as such, you have a lot of inherent noise from other tenants. It is even more noisy under failures and stragglers. So the straw man solution to get around these problems is to run multiple times and take the average. The good thing, though, is that Bayesian optimization is good at handling additive noise. So in this case, the only thing that you need to do is to merge the noise in the confidence interval that you already built. The noise could also be learned by monitoring the cloud or using the historical data available in the cloud. But the challenge here is that the noise, the dominant noise, is actually could be multiplicative in the cloud. So as an example, imagine that you have a VM that has an iOS slowdown, 20% iOS slowdown due to overloading. If you have 1 gigs of data that you want to run to the disk, and it normally takes 5 seconds, because of this 20%, now it takes 6 seconds. The same thing when you go to 10 gig, if it took 50 seconds, now it takes 60 seconds. So basically, instead of modeling the cost function as a normal without any noise, we just multiply a noise factor to this cost function. Now, if you remember, I said that Bayesian optimization is good at handling additive noise, but here our noise is multiplied to the cost function. So to get around this limitation, we just take the log and optimize the log of the cost function to get around the noise. We also did a few other modifications. Like for dealing with the large searching space, we did discretization. This helped us avoid a lot of config that are invalid, and it also helped us speed up the searching process. For example, your CPU frequency is usually a continuous interval. By breaking it down into high frequency and low frequency space, you basically avoided asking Bayesian optimization to optimize across a continuous space. We also modified the stopping condition of Bayesian optimization to allow trading of accuracy for searching costs. Basically, we expose the knob of expected improvement in the acquisition function to the user so they can decide how close they want to get to the optimal config. Finally, BO is very good at interpolation, but it has trouble with extrapolation. So to give a full view of the searching space to the Bayesian optimization, we use the quasi-random search to uniformly explore the space before Bayesian optimization kicks in. For evaluation, we used 5 big data benchmarks covering database, MapReduce, and machine learning applications. These applications have a variety of resource usage. For example, they use different amount. Some of them are are resource bottlenecked by CPU. Some of them are bottlenecked by RAM, and some of them are bottlenecked by disk speed. We tested these 5 applications on 66 well-chosen configurations with a variety of settings. For example, for our RAM, our clusters go up to 800 gigs of RAM and hundreds of cores, 100 core. So for the metric, we measure 2 metrics: the accuracy, which is the running cost of the configuration we choose, and the overhead of finding such configuration, which is basically the cost of searching for that config. We compared against both searching and modeling solutions. For searching, we compared against random search and coordinate descent. And for modeling, we compared against earnest. Now let's look at TVCBS, which is a database benchmark, to see how different approaches compare. The y-axis here is showing the running cost normalized by the optimal configuration, the one with the lowest cost among the 66 config that we ran. And the x-axis shows the normalized searching cost. the searching cost is normalized by CherryPick. And by the way, the lower, the good searching solutions lie on the bottom left of the bottom left corner of this graph. So let's now look at the searching solutions. In this case, I'm showing you where the random search lies. So as you can see, random search has a lot of error, even though we are giving it different budgets. So on median, it has 25% error. Coordinate descent does better than random search. On average, it has 25% higher searching cost than CherryPick. But the 90th percentile of searching cost can spike to 300%. Also, the running cost of coordinate descent on median, it finds the optimal config, but it can spike to 75% higher overhead for running costs. Basically, the coordinate descent is not stable. So searching solutions are not accurate or they're unstable. We also looked at modeling approaches. So in this graph, the errorness, which is the green circle to the bottom right of the graph, has high accuracy in this case, but it costs 3.7 times more for finding a good cloud config. So it is hard to make modeling solutions adaptable. We also compared CherryPick against the guidelines that cloud providers give, in this case, Amazon. So for the machine type, we looked at the same TVCBS application, and since it's a database application, AWS recommends machine types from R3, I2, and M4 families. But in our scale, we found that CherryPick suggests C4, and that's actually the best configuration for our database workload. For cluster size, AWS basically has no suggestions. And in our experiments, we found that choosing a bad cluster size can have up to 3 times higher running cost, higher cost than choosing a right cluster configuration. Once you consider both factors, it even becomes harder to know what is going on. So to wrap up the talk, I would like to say that picking the best cloud configuration is critical for recurring jobs. An ideal solution will work across all applications and has low overhead and high accuracy. To work across all applications, CherryPick uses Blackbox Modeling, which requires running the cloud configuration. But because it aims to have low overhead, it can only run a few configurations. When these things happen, a common machine learning rule is when you have limited amount of information, instead of solving the general problem of modeling everything accurately, you would solve the immediate problem, which is answering your immediate question, which is finding the best cloud configuration. So to wrap up, if you need to pick a good cloud configuration, please feel free to try our tool, which is available on GitHub. And thank you. Okay.
Hello. Thanks for the presentation. I have a quick question. Can you go to the slide?
Can you introduce yourself, please?
Yeah. This is Merdad from University of Michigan.
Okay.
Can you go to page 37?
37. Sure.
So I can see that your solution is actually faster than existing solution. But what is the absolute overhead of running the brute force approach?
So the absolute, let me put it this way. In this case, the point that I'm showing, CherryPick only runs 6.6 runs on average to find the best config. So it only explores 10% of the total space before it can convert.
So I want to know how long does it take to run the brute force approach for this configuration? Because you have the normalized.
Right. So running the brute force approach for this test case, I think it took around 12 hours, 12 to 24 hours, okay. Yeah. So running it on all the 66 config. And we parallelized some of it. So we were running, I think, 4 configuration at a time because that was the quota that we had from AWS.
Okay, okay. Thank you.
Hi, Pratik Sharma from UMass Amherst. I'm wondering what the role of the prior is in the Bayesian optimization, and how do you pick a prior in general?
So that's a great question. So basically, the role of the prior is that it puts the role of the prior is basically that it puts a assumption on the shape of your space, right? So there are different priors that you can use. The one that almost everybody uses is a Gaussian process prior. And the reason for that is that it's a tractable prior. I haven't seen any framework that gives you other options. But basically, the role of the prior would be that it gives you, it tells you how your space looks like.
Right. So is that based on a preconceived application performance? So is the prior based on a preconceived application performance model, or is it only a...
Yeah, it basically, you basically, based on the prior, you basically tell how smooth, for example, in the case of Gaussian process, you're telling it how smooth the space can look like. You also have the kernel function, which basically sets it up even more, but the process basically, in this case, tells you how the range of confidence interval changes.
Thank you.
Yeah.
So I had a question. You discretize a bunch of stuff to get the Bayesian optimization to behave itself. What happens if I don't want you to?
What happens if you...
If I don't want to discretize, if I measure CPU cores in fractions of a core and byte and memory in bytes?
That's a great question. So Bayesian optimization, basically, if you don't do... First of all, the question is, why don't you want to do that? Because if you have all these fine-grained stuff...
I do.
I'm not arguing, right? But I'm just saying, if you don't have all these fine-grained stuff, it might be enough to discretize at the level that you're interested in. Like basically,
milli-cores. Milli CPU cores.
Right.
A thousandth of a core.
Right,
yeah.
thousands
Okay,
of cores,
right.
But basically, the way that you would handle it is that you can do it in 2 levels, right? So basically, or multiple levels. Basically, you would have space divided into maybe 250 cores, 250 cores, 250 cores, and find the region that your good solution lies in. And then you run Bayesian optimization on that space again, and you do it iteratively. That's one way of handling it, if that answers the question. But in general, at least at this scale that we think, it's enough to, like, if you're Google, you probably need to do it in multiple levels. But if you're a normal user, you might not need that because Bayesian optimization works pretty well.
Sure, I'm just thinking of the adage you offered, which is go solve the problem you have rather than something else. I was thinking of the adage you gave us at the end, which is go solve the problem you have rather than something else.
Right.
Okay, thank you.
Cool. Great. Thank you.